Thanks, everybody. Good morning. So I'm going to be talking about connecting free-floating planets with the tail end of the stellar IMF. And as we know, this is important because the planet mass function gets to pretty high masses. The RV planet population goes up to 20 Jupiter masses, so that's overlapping with brown dwarfs. And as you go out to larger distances, we know that the planets go up at least to 5 or 7 Jupiter masses and probably a lot higher if the individual companions that we see form like planets, which is yet to be determined. So what I'm going to do is talk a little bit, just briefly, about the closer in planet population and at those high masses. And then I'm going to go ahead and talk about the more distant population and the potential for gravitational instability population of planets, which is what I think most of the rest of the session is going to be about. So I'm just starting here with this plot, this very nice plot of known planets. It's pretty busy, but busy in a way that I expect those of us in the room enjoy. And the reason I put this up here is because these plots really frustrate me, even though it's a really nice plot, because it stops at 33 Jupiter masses. And the planets don't stop at 33 Jupiter masses. They're hanging out. Can you see is there a pointer of some sort? And okay, they're hanging out. The orange ones are hanging out at the top. Let me see if I can get rid of this. Okay. The orange ones are hanging out at the top between 1 and 10 AU, pushing up against the bounds. On the right, the imaging planets are definitely pushing up against the top bounds of this plot. You know, maybe over on the left where the hot Jupiters are, it's not so bad. You can actually see a gap there. And we do know that the planets and the brown dwarfs are not the same population. Thank you very much. This is a classic paper about the brown dwarf desert. You can see but interior to something like 100 days. Here are stellar companions up here, planets, and there's a desert of brown dwarfs in those close-in separations, and that has stood the test of time. But it's less clear what that looks like at larger distances. And in particular, you don't even have to go out that far, out to 1 to 10 AU, where you again start seeing it. So I'm going to start briefly talking about these orange planets between 1 and 10 AU, and then I'm going to go on to the direct imaging objects. All right. So we heard a lot about planet-planet scattering yesterday and its ability to eject. And we also heard, and Hagai emphasized, that if we're going to understand the ejected population of planets from scattering, we actually have to understand the population that remains as well. And this is the observed population of eccentricities as a function of planet masses for the RV planet population. And I want you to notice this pretty weird thing here, which is that the high eccentricity ones are actually the high mass planets. If you run a simulation with a bunch of planets, you're going to eject the low mass ones more easily. But if you look at the observations, the high eccentricity ones are actually the ones that are at high mass. And you can actually get this result by keeping in mind that if you have a collection of planetary systems, they're not all in the same system, right? So some systems will have more planets, they'll have more mass in planets, they'll produce higher mass planets, and some will have less mass in planets, they'll produce lower mass planets. And if you recall again from yesterday that the close-in planets end up colliding and the distant planets end up ejecting, and there's a little bit of a difference depending on your planet mass where that boundary is, but really it's about how close you are to the star versus how far you are from the star, not about what your planet mass is. If you're close to the star, you're deep in the potential well, you can get excited up to your escape velocity, you can excite your neighbors to your escape velocity. But that's not high enough velocity to escape the system. At large distances, it is high enough velocity to escape the system. So no matter what mass you are, you're going to be colliding close in and ejecting far out. And that goes for giants too. And in all of the planet-planet scattering simulations that people do, you end up with collisions for close-in planets. So I'm not going to go through this whole project, but I'm happy to talk with anyone about it more later. But what we did was we just made the somewhat bizarre, but only one bizarre assumption that you can start with a number of giant planets close in to your star. 5, something like that. It's not that crazy. You know, the super Earths, you make peas in a pod. If you make them a little more massive peas, they become above the critical core mass for instability, and you make a bunch of giant planet peas. Anyway, if you make this assumption and basically tune nothing else at all, other than picking the mass distribution of disks that gives you the mass of observed planets, you can get this behavior. The high mass systems make higher mass planets that are excited to higher eccentricities. Look at it in semi-major axis, in metallicity. It actually looks surprisingly great given the lack of any tuning that we did for this. So I think there might have been a giant impact phase for giant planets. And if you take that seriously, then as we all know from understanding planet-planet scattering, you have these collisions in the inner part of the disk, and then you have scattering and planet ejections in the outer part of the disk. And the prediction that this makes is that the mass function, not the number of stars with planets of this mass, but the mass of the maximum masses that you make, peaks at between 1 and 10 AU, about 1 to 8 AU. So that's where you should get the highest mass companions, and out farther at more distant distances, you don't get as high mass companions. And this whole population here is leading to ejection as far as you can take it, as far as you actually make the planets out in the disk, which we don't know exactly how far that is. But you can make, but the key underlying idea here, right, is that you make a bunch of low mass giants. What's low mass? 1 Jupiter mass. That's not that low mass. You can collide that a bunch of times to get to 20 Jupiter masses. And the direct imaging surveys can't see 1 Jupiter mass planets at any distance. So they can only see above 2. And that's actually being conservative because it's assuming that you're using a hot star formation model. So anyway, this prediction, Haggai's prediction from yesterday, what we need to do in order to understand where our rogue planets are coming from is to really connect them to the remaining planets that have not gone rogue. And so I think it's worth making qualitative predictive models like this for a variety of formation models, and we saw some of that yesterday as well. Okay, so this mass function peaks at 3 AU. This is nice for microlensing because you can see the companion stars for these, and then out at the larger distances. Those are the ones that look like the rogues, so it should be possible to test this. And if this isn't what's going on, that's fine with me. I would like it to be tested. Okay, so now let's go to the larger distances, where we start looking at planets that we think may actually be forming the way that that stellar mass companions are forming. And out here, we definitely have the top of the plot cut off. And what I'd like to do is look at the IMF, the mass function that we were looking at yesterday. And I'm looking at this in a version that was recently published by Yi and Kenyon. And just so everybody's on the same page, the mass function is being modeled as a stellar mass function and a planetary mass function. And of course, the brown dwarfs are in the middle here. So here's the plot, the summary plot from their paper. It has the SUMI result that we saw yesterday on here. You can see, and the blue is the Gould result. And let's just take a look at the features here. So in the SUMI result, less than 1 Jupiter mass planets dominate over the stellar mass function. It matches the Kirkpatrick 20 parsec local census up in this region here. The Gould result changes to planets at less than 6 Jupiter masses. It matches the Chabrier result up here. I assume you all will figure this out with Roman. I'm not worried about it. The key point here is that for both of these models, they've got a similar planetary mass function. And if you look at this region in the 5 to 13 Jupiter mass range, both of the populations, and this was the point of this paper, are consistent with the direct imaging results, meaning that there's a 1 to 2% likelihood per star of having a planet. And that's on these dashed lines here. So it's assuming that the ones that are part of the stellar population are not going to be bound. These authors argue that, in fact, these can be, and they actually may have to be all bound and not rogue planets in order to match the direct imaging statistics. Just to take a look at the statistics from the direct imaging real quick. These are the 5 to 13 Jupiter mass planets. This is the occurrence rate. These are for AB stars. We've got, several percentage points here. For the FGK stars, very low. So when we talk about the number of companions that you have per star, you actually have to know what kinds of stars you're talking about. And so one of the things that you have to do is to convert these numbers to the per total star and try to look at apples to apples. And that's what the Yi and Kenyon were doing. So just it's worth remembering that not all host stars are equal for these stats. This is not really relevant to my point, but as a side note, if you look 2 to 13 Jupiter masses, the rates for these AB stars do go up substantially, though it's still pretty small for the FGKs. Okay, so that's the direct imaging. Okay, so we had the question yesterday, how is this consistent? How is having 1 or 2% likelihood per star of these giants consistent with the 20 planets per star that we're hearing about? Well, this number goes all the way down to 1/3 of an Earth mass, and it's actually consistent with this number. It's just that you have most of your planets are at the lower masses. So if I'm saying something wrong here about the observations, I hope somebody will call me out on it in the question section, because I would like to learn that I am saying something wrong rather than just continue to say something wrong. Okay, so this is consistent. You can have a lot of planets per star, but it's still consistent with these things right here in the middle being all entirely bound, according to the direct imaging observations. Okay, so notice that if you're using this kind of model that's just the stellar IMF and the planetary IMF, then the stellar IMF here has to go all the way down to a Jupiter mass, which is similar to the opacity limit for fragmentation, where you can't fragment in a cloud anymore because you're too opaque. It depends on your metallicity, but for the Chabrier IMF, the Gould one, or even lower mass here. I mean, I guess you don't have to go all the way down here because this is an extrapolation, but Jupiter masses as part of the stellar population. And that may be the case, but it's at least not, standard, at least not fully agreed by the field that it's the case. This is an argument from a recent paper by Krupa et al., saying that below 10% of a stellar mass, which is quite a bit higher than that, there are different binary fractions and separation distributions. And that means that they think that direct fragmentation of a filament is rare. And so they argue for peripheral fragmentation, which mostly means gravitational instability in a disk. And this is, so again, that's quite a bit higher mass. So if we go on to this plot, that goes all the way over here. And so, in this region here, maybe we really need a third mass function for the gravitational instability objects. And we know that the idea of gravitational instability planets has been around for a while, ever since at least the year of Titanic and Candle in the Wind. And is mainly disfavored, right, because it makes massive wide separation objects, which we now know exist. So, so more work is merited in this area, as I'm sure Sergey would agree. I don't know where he is right now. Anyway, so here's a plot, from almost a decade ago, showing some planets, some brown, some RV and some imaging objects, and you can see there are a bunch of objects that are massive and at wide separations. So why not? Why can't we make them by gravitational instability? And I'm just going to go to a quick reminder of why pre-exoplanets we thought that the structure of our planetary system is the way it is. It's still, useful information, right? Rocky planets in the middle, gas giants, ice giants. We start with cloud, collapse into disks around young stars. You have gas, dust, and ice. Material is falling onto the disk, being processed through it. In that disk, solids collide with each other. If you have more material, they grow faster. If you're farther from the star, they grow slower because it scales with the orbital time. So you sort of look at it schematically. Close to the star, you just don't have very much stuff, so you make puny rocky planets. A little farther away, you have a larger area on the screen, and you also might have gone past the ice line, so you have more stuff. So you make cores that can grow into gas giant planets, and you go even farther away. And you don't have time to make those massive cores before the gas just dissipates. The planet's gravity dominates within its Hill radius. So that's where its gravity dominates over tides. And so you can make an isolation mass planet. And again, this is all pre-exoplanets, where you accrete all of the gravitationally accessible material from the disk. And if you can't replenish that material, you can accrete from within several Hill radii. And so then you can go back to our schematic here and see that small isolation masses in the inner solar system leads to isolation masses that are smaller than the Earth. So you need a late stage giant impact phase to complete your growth. Whereas out here, the isolation mass is just small enough that runaway gas accretion takes a long time. But we all know that, that a lot of these assumptions that have gone into this have changed since the discovery of exoplanets, and a lot of work has been done on how gas interacts with solids and disks and changes these growth processes. And one of the main early drivers of this, and still an icon because it hasn't been reproduced, is the HR 8799 system, wide separation giants, and Neptune's orbital distance is on here, and these are about 5 to 7 Jupiter masses. And these things just do not conform to that model at all. They're way too distant, they're way too massive. So then we come to the 3 ways to form companions, turbulent fragmentation, core accretion, and we also need to include gravitational instability. And we can already just cross the regular star formation version off for HR 8799 because there are 4 planets orbiting a host star. Turbulent fragmentation doesn't do that. It makes hierarchical multiples, not things with multiple things going around in a disk. Okay, so can you make HR 8799 this way? I'm going to say some old stuff, then I'm going to say some new stuff about HR 8799. So I'm going to say some really old stuff, then I'm going to say some new stuff. Yes and yes, you can make it either of these ways. So you can make it by pebble accretion. I'm not going to talk about this, but really you can increase your cross-section for accretion by up to 4 orders of magnitude by including gas drag. Bring in your small solid pebbles. Their relative velocity with your core is damped by the gas. It gets captured dynamically into orbit, spirals in. You grow much, much faster. It can be embarrassingly fast. It can be a problematic fastness. Suddenly the problem became the opposite. Okay, fine, you can do it. All right, what about making HR 8799 by gravitational instability? You can do that too. This is from 2010, so that's why there aren't very many points in this plot. But here's here's our planetary companions, brown dwarf companions. Notice how HR 8799 in this distance mass ratio plot sits right in between them. And so you can ask, is this more like the planets or is it more like the brown dwarfs? And I just want to highlight that gravitational instability is possible with observed disk masses. There are a number of different techniques that are really pushing the quoted masses for observed protoplanetary disks closer to gravitational instability. This one is one that has to do with dust lines, but there's also measurements for a few disks with HD and with multiple lines. They're massive enough, some of them at least. Okay, so gravitational instability, the most unstable scale is about the scale height of the disk. You can go ahead and plug that in. For HR 8799, you get a minimum fragment mass. You can't do it too close to the star because these fragments can't cool fast enough, but the masses of the planets are close enough as long as they don't grow. Okay, so you can do it. So this is I dusted this off from a long time ago. What happens if you collapse in a disk around HR 8799? If you collapse during the infall stage, you don't get to just turn your disk gravitationally unstable randomly and run your simulation. It has to have been driven there from accretion onto the disk. You keep accreting, you make a stellar binary. But if you make your disk and then right at the end, you gravitationally collapse, then you open a gap, you turn off your accretion, they migrate in, they go into their mean motion resonances that we know they have to be in to be stable, then hooray, you can get happy times. So nothing about that is a problem, but it does have to be a very specific situation. And so we argued at this time that gravitational instability planets should be failed binary stars. And you know, some of these things, if you make them by gravitational instability in principle, can be driven closer into the disk, and maybe Sergey will tell us about this. But you should still be making higher mass things as well, because it's very easy for them to accrete once they've collapsed. Okay, so that's some old HR 8799 things. Here's some new things. This is some spectra from JWST. Aren't they gorgeous? This is from Jerry Schwann and Yagari Chitan doing some modeling with this. And what they found is that they can constrain the carbon, oxygen, and importantly, sulfur abundances in the 4 planets across this disk. And what's nice about this is that sulfur tracks solid accretion because you expect the sulfur to be in the solids in this environment. So what we did was we showed that if we took the sulfur and see, there's a trend. There didn't have to be a trend. I have to emphasize, this didn't have to make any sense. And what's beautiful about it is that it makes sense. You take the solid accretion measured from the sulfur, and it matches both reasonable pebble isolation trends or reasonable planetesimal accretion trends. And then you still need to add more metals on top of that. And the amount of metals that you need to add on top of that is consistent with the same pebble flux for the whole system, increasing the mass of solids in your disk. And it all works, and it's beautiful, and I love it so much. And these things are very metal enhanced. Metal enhancement, I would argue, means they formed in a disk, but it could still be pebble accretion or gravitational instability. You can't really tell the difference between these because a lot of the metals are coming from the gas, and you can always accrete some solids after the fact from planetesimals. Even giant planets, this is from close-in. I'm running out of time, so I'm not going to go into this, have substantial metallicity. And if you look at the star formation models, though, having even solar metallicity, this is from Matthew Bate, makes it harder to fragment at lower stellar masses, lower masses. And it's a lot easier to get these planetary mass fragments at lower metallicities. So metallicity is going to be a useful way to try to tease this out. Okay, I'm going to come back to this plot. Gravitational could be fragments, brown dwarf desert. I just want to show two other recent plots and then make some comments. This is from Gaia, looking at the brown dwarf desert. This is 100 days. This is the driest region from Mange of the desert. So between like 40 and 60 Jupiter masses within 100 days. Out here, that doesn't actually look super deserty. That said, and this is not this has a lot of selection effects in it. There's another recent paper, also from Gaia and RV, Hipparcos-Gaia combinations. The overall structure of this shouldn't be taken too seriously because it has too many selection effects, but they do see the brown dwarf desert even out at larger distances. So, so we really need to try to understand, if we want to understand what's happening with all of these formation models, where the population connects to the stellar population and where it doesn't. You know, out at 10 AU, is there a desert or is there not? Is this connecting to brown dwarfs forming as part of the star formation process through this gap, or is it not? And I really think that this is the way that we're going to figure out which of these processes is dominating the formation of high mass planets at larger distances, and by extension, the rogue worlds that they're kicking out. Okay, so if you know me, you know I'm going to say, but I always am going to say, please don't cut up your plot at 33 Jupiter masses. Come on, we wanted to go all the way up to 100% of the stellar mass to see it. 100%. Microlensing folks are used to doing this, but when you get more data, you might feel like tempted to make a planet plot, but don't do it. Make it go all the way up to the stars. That's how we're going to find out what's going on. Don't do it. Goes all the way to the stars. Okay. I'm going to end there. I'm not going to say my last thing. I'm out of time.
Excellent talk. I really liked it. So the point about direct imaging results having very few gas giants and also brown dwarfs at wide separations, it's really been overinterpreted because actually modern GI simulations don't even predict planets there. It's very difficult to make them stop at wide separations. We want to be at a few AU. You know, that's how efficiently we migrate. So it's entirely consistent with every disk around every star producing many GI fragments initially, you see, and then we're evolving either by migration or into the massive companions regime, or in fact being, ejected. So.
Yeah, and I'm sure you'll agree with me that more work should be done on what that distribution actually looks like. And I think I would say that the key thing is that that population will be anchored at the outside, while core accretion population should be anchored at the inside. And I think that there's no reason that they can't both be going on. And we should be able to tell empirically. I think we could always be very unlucky, but I think we would have to be quite unlucky for there to be no clear crossover point, as long as we look across enough dimensions.
I have a question here, Ruth. Can you go to the JWST plots of HR 8799,
Sure.
the ones that show the metal?
Yep.
The questions I have, so do you know how the carbon, oxygen, and sulfur were measured out of the data and what they're using for the brown dwarf C and O there?
The brown dwarf was an average of 8 brown dwarfs that I don't know which ones they were, but I can tell you after at the break if you want to know.
Yeah, because our team has done a ton on this plot on getting the carbon, the oxygen, the sulfur, any of it. And it's really important whenever you do this to do oxygen sequestration because that's stuck in the clouds. So we should talk about this plot. And it's just, I know it seems exciting to use the metallicity, this, like look for the chemical signature formation, but it's such a careful atmospheric.
I totally agree. And, this is, I mean, these are hot objects. I would definitely like to talk to you about it. It's at least better. I mean, you know this, but for everyone else, it's for these hot objects, it's at least better than for, actual Jupiter, where the oxygen is completely sequestered and we have no idea what it is. But I would be delighted to talk with you about it.
All right, let's thank Ruth again.